Prospect 101 students, and welcome to Module 4, Learning Objective 4. This will be the final learning objective from Chapter 5, and we'll talk about how you perceive depth and how objects remain constant. Okay, come on. Here we go. So we have two types of depth cues that we use in order to see, the world in 3D and in order to see depth and judge distances. We have binocular depth cues and monocular depth cues. So binocular depth cues are cues of depth perception that arise because people have two eyes. You need to use both eyes in order to use a binocular depth cue. Binocular depth cues tend to help us judge the distance for things that are not far away. Things within a few yards, especially things that are in close proximity. Like, think about how, if you reach for, let's say, a coffee cup on your table right now, or you reach for a pen, like, you don't miss it sometimes. Like, like exactly how far it is, exactly how far to move your arm to pick up that pen or that coffee cup. I mean, like, you could, try it now if you want. You could do it over and over, like, without missing. Like, it's our binocular depth cues are really helpful for close objects. They give us like great information exactly how far you have to reach to pick something up, or to kick a ball, how far you have to kick your leg, or something like that. Monocular depth cues are cues of depth perception that are available to each eye alone. So you can see these using only one eye. They're also known as pictorial cues because they're used by artists to create a sense of depth in their pictures. Let's look at one binocular depth cue in a little bit more detail here. And it's known as binocular disparity. We use both eyes to perceive depth through binocular disparity, where each retina has a slightly different view of the world. So if you hold hold a pencil or a pen up, like, maybe a foot away from your face, and look at it, close one eye and look at it, and then close, your other eye and look at it. So look at it with your left eye and then your right eye, and you'll see that you get a different image. It appears at a different point compared to, like, if you see back, it'll seem like it shifts against the background, whether there's a wall behind you or whatever, behind it or whatever, like, or your screen's behind it, but it'll shift. And you actually like see slightly different angle of the pen or pencil. You could position it so that one eye could see the words on the pen, but maybe the other eye can't. Anyway, so you're getting it because your eyes are spaced apart a little bit. You get a different angle and a slightly different view of objects. Once again, this is not really going to work for things that are far away. Like, if you're looking at something half a mile away, I mean, you're not going to really get a different view in each eye, because it's just so far away that you're not going to notice the difference in angle. But for things up close, it makes a huge difference. You get like a huge shift, depending on so each eye gets a different viewpoint, and we use this information to judge how far away it is. If something's farther, like a little bit farther away from you, then you get less of a difference between the two eyes. If something's closer to you, you get more of a difference. And your brain uses this information to calculate how far that object is away, which is why we're so good at reaching for something like, that's a foot away or a few feet away, or kicking a ball or whatever, and not missing. I mean, because we automatically use this without having to think about it. But the brain makes rapid calculations to figure out exactly how far away an object is. As an example, if you go to a 3D movie, you wear specialized glasses. and these glasses are polarized to allow different types of lights through. So each eye ends up seeing a slightly different version of the film, which is what those glasses do. Usually you have like, I don't know, often like one of the lenses like looks red and one looks green. I think I'm not, it's something like that. But it's been a while since I did one of those. But I mean, it's like you it's creating binocular disparity, even though everything you see on the screen is the same distance away. Like it's a flat screen. So in order to get the real sense of something coming out of the screen towards you, it creates these two different viewpoints, um, taking advantage of how we use binocular disparity, and it creates binocular disparity by showing you two different versions of the film, one to each eye, and so you get the sense of like a monster coming close to you. Okay. This is a little bit more technical on the screen of what's happening with binocular disparity. Use both eyes to perceive depth through binocular disparity, with each retina having a slightly different view of the world. As it says here on the screen, the visual system sees every object from two distinct vantage points. The distance between retinal images of objects A and B is different in the left eye from the distance between A and B in the right eye. This is an important cue for depth. So, because B is a little bit further away, and because your eyes are looking at A and B from different angles, you end up with a very short distance between A and B in the left eye retina, but a longer distance between A and B in the right eye. And once again, our brain makes rapid calculations to figure out, like where A is versus B, and once again, this is not going to be things that are really, really far away, but it's going to help me, if I've got a set of pens. Actually, I have a set of pens on my desk in front of me. I've got different colored pens, and I got like 4 different colored pens here, and help me reach for the for and not miss the pens, even though they're different distances away. One's closer than anyways, but it's once again, my brain makes these rapid calculations because I'm getting a different image in each eye, and it just tells me, exactly how far each thing is away. Not in a sense of numbers. I'm not good at judging distance. I don't know, they're about a foot away, but my brain makes um, more exact calculations than that, and so I can pick up the black pen when I want, or pick up the green pen or the red pen. Okay. Anyways, let's go on. That is known as binocular disparity. It is a binocular depth cue. Um, we're going to move on to the monocular depth perception. And you can perceive depth, as I said earlier, with just one eye. And in this image, for instance, there are 6 monocular depth cues that we're going to talk about. Remember, they're also called pictorial depth cues, and they create the illusion of distance. Obviously, everything in this picture on the screen is exactly, the same distance away from you. Like those, those small guys at the back, yeah, on the, waiting on the corner of the street are just as far away from you as this guy in the white shirt and tie over on the right side, like, because it's a flat screen. But you get the sense of depth. You can see what's farther away and what's closer in this picture. But binocular disparity is not going to help you here, because everything in this picture is exactly the same distance away, because it's a picture. It's a flat screen. Okay, so let's go through these 6 monocular depth cues. The first one is known as occlusion, and it's a very simple one. If one thing is blocking another thing, then the thing that's blocking it must be closer. So, as it says here, a near object, this woman's head in the green coat, um, blocks an object that's farther away in the building. So part of her head covers up this gray building at the back here. That means that she's closer to us than the building. You know, this guy in the white shirt is closer to us than this black car behind him because he's blocking part of the black car. That's all occlusion is. If something blocks something else, it's got to be closer. Okay. Height and field. Objects that are lower in the visual field are seen as nearer than objects that are higher in the visual field. So I'm going to use my red pen here. So this guy here is standing here. I'm just going to go where their feet are. These three people are standing about here. These people back here are standing here. So you can see the ones that are farther away, they're higher in the visual field. Like this red line's higher up than these red lines. Something that's, and if I go to these people way back here, you see like the red line would be about there. So like things that are farther away, they're gonna, like the ground is gonna be up higher if something's farther away. And so the image of that person's gonna be up higher. So like if you ever trying to draw depth, I mean, and let's say you're drawing trees. So if I just draw over here on the right, I'm just gonna try to whip off a tree here. Let's say, okay. So I draw a tree here, and then let's say I just draw another tree here. I mean, right away, and I'm not drawing well. This is not much of a tree, but you can see that like this tree, you get there's a sense right away. This tree is further away than this tree. The one on the right is further away than the one on the left, and this is due to height and field. This one starts up higher than this one, so it must be farther away. Okay. Let's go on. Relative size, objects that are farther away, such as the man on the sidewalk back here near the sea. He's got a black briefcase. Projects a smaller retinal image than close objects of a similar sized man on the street near B. Okay, so they're comparing this guy here to this guy back here. And what relative size tells us is, well, we know these are both adult men, so they're approximately the same height. Of course, there could be up to a half a foot difference, but generally speaking, they're adult human height. So we kind of know they're probably each somewhere between like 5.5 feet and maybe up to 6.5 feet, but they don't look that tall. But anyways, but what you see is that so we assume that they're about equal in height, but this guy, see, like it takes this much, it's got this much height that comes into our retina. This guy's got much smaller height, so he must be further away. These are about the same size because they're both adult men, and yet this one projects a much bigger image than the guy in the white shirt. And so this guy in the purple shirt must be closer. So that's relative size. So if you know that two objects are about the same size, but one of them appears to be smaller, it must be farther away. Once again, these are probably all seem like really obvious things, but we use all these things all the time without thinking about it or knowing about them. We have familiar size. We know how large familiar objects are, such as a car, so we can estimate how far away they are by the size of the retinal images. So they're mentioning this car beside D back here. So we know how big a car is, and so it makes when it makes a certain size image on our retina, it gives us a clue as to how far away. If it was made a smaller size, like this car back here, this orange car back here, this would make a smaller size on our retina. Well, that one must be farther away. So, like, anyways, when you know how big something is, then the size that it appears tells you how far away it is. Okay, linear perspective, seemingly parallel lines appears to converge in the distance. So they're talking about the sidewalk back here. So if we look at the start of this sidewalk, I draw from one side to the other, it would be kind of like this. If we go really far down here, And I don't know, let's say here, I draw from one side to another. This second line is going to be smaller than this first. And it's like looking at, this is not a great example here, but it's like looking down a set of train tracks. Like I'm going to draw it over on the left here. Like they appear to kind of go like this. Like up close, it seems really like they're, kind of wide apart. But if you look like, if you can see really far along the straight set of train tracks, they'll seem to converge in the distance, almost like they come to a point. Let me just, I guess I'll make these look more like train tracks, but like as it goes off in the distance, the lines converge. They don't, even though we know they're parallel. So this gives us a clue as to how far away we're looking, depending on how close the lines get. The closer they get, the farther away the point is that you're looking at. Okay. Texture gradient. As a uniformly textured surface recedes, its texture continuously becomes denser. The pattern on the pavement, for example. What they mean here is that as far as denser, it becomes becomes less detailed. It's an easier way to think about it. So look at the pavement up close here. It's close, kind of where this is as close as we can get. Like you can see in these white lines, for instance, there's a bunch of little black splotches all through them and stuff. But if you look at this white line, let's say back here near this D, it looks like uniform white. Like there's no black splotches or cracks in that. It's only because of texture gradient. As you look further away, you can't see the details, on a surface, such as a road. Up close, the closer something is, the more details you can see. The further away something is, the more uniform it becomes. It's like this road just looks like solid gray back here. Up here, we see it looks kind of like, there's some black in the gray. An easier example, one I like better than this picture, is think of standing in a large green field of grass, and and if you look straight down in front of you, you're going to notice individual blades of grass. You're going to see there's some places where the grass is missing, like there's some, it's not growing. There's like little holes where there's some grass not growing, and you'll notice like a whole bunch of little details. And as you start looking further and further away in the field, you'll see less and less details. And if you're looking really far away, you won't be able to make out any blades of grass. It's just going to be this uniform green. You know, it's like there's blades of grass, but you can't see them. So the further away you're looking, the less you see it as far as the texture of the surface. This works with carpets too. If you're in a carpeted room, you look down at the carpet closer to you, and you'll see like little colors and details in the pattern, maybe and little imperfections. And as you look further away, all these details disappear if you're in a big enough room, and it'll look different up close and farther away. This is how texture gradient works. Okay, let's go on. Those are pictorial depth cues. They could ask you about any of these on the test, so make sure you do try to keep them apart. And I'm going to erase everything I drew here. Okay. Going on. Object constancy. Correctly perceiving objects as staying the same in their size, shape, color, and lightness across viewing conditions that yield different physical input to the eyes. Things are constantly shifting in our visual sensation. If let's say you're walking, a person walk away, they're going to get smaller and smaller in your retina. The sensation is going to change every step away they take. They're going to make a smaller image on your retina, but they're not shrinking. That they're the same size, whether they look really small because they're far away, or they look big because they're up close. Like that would be size constancy, for instance. So like just to go back, um, it's kind of it's similar to the relative size. Like this guy up here in the white shirt, like he looks like twice as tall as this guy back here in the white shirt near C, um, because he's closer. Like so, but because of size constancy, we know that they're going to be approximately the same size, give or take half a foot, maybe up to half foot difference or so. But especially like if it's the same person walking, like if it's the same person and they move about, they get further away or closer, the image is going to keep changing in your retina. It's going to get smaller, it's going to get bigger, and but you know that they're always the same size, so you compensate for that. That's all that size constancy is. We also do this for shape, color, lightness. I don't love this car example, but let me read what they say about it here. The image on the retina is vastly different for these four images of a car. Because you know how large a car normally is, knowing how far away the car is from you lets you maintain size constancy. Knowing the angles you're seeing the car from enables you to maintain shape constancy. The shadows help maintain color and brightness constancy because they suggest the angle of lighting, and you know that light makes colors brighter. And it's anyway. So, as far as something like let's, I'll just deal with this last one first. Um, there's you know color and lightness constancy. Under different viewing conditions, the shirt I'm wearing now, for instance, will look like a different color. Like under certain lighting conditions, it's going to look darker, and under certain lighting, if I'm out in the sun, it's going to look lighter. Compared to if I'm inside and it's in a darker room, and the color can even change if depending on whether what types of lighting there is, like under different viewing conditions, the color of your shirt might change. So like, and if you're watching this, you're watching somebody move through different conditions, or you're watching a car drive through different lighting conditions, obviously the color of the car is not changing. This is what object constancy is all about. You know that just because the the sensation is constantly shifting for size or for color or lightness or for shape, you know that the objects aren't actually changing. And so your brain compensates for these things. This car here, even though it looks brighter in the second picture compared to this first picture, I mean, we know it's the same color, the shape constantly seems to be changing depending which angle we look at it, but we know it's always the same shape. Let's look at a few more examples. This is a pretty straightforward one for shape constancy. We perceive a door as a door, and we perceive it as a rectangular door, whether it actually appears as a rectangle. So when we're looking head on to a door, it actually does make a rectangle. You would have to be like, straight in front of it, looking at it straight on. But as soon as, like, if you're looking at it from some kind of angle, like the door's opening or something, this pink shape is called a trapezoid. It's not a rectangle, but you still see the door as a rectangle. Like the image that's hitting your retina is not a rectangle anymore. It is a trapezoid. Um, but if I asked you what shape it is, you would say rectangle. So we don't rely on on the raw data. This is like where sensation and perception differ. Your sensation would say, "Oh, the door has changed shape," as it opens up. It used to be a rectangle, but no longer is it. But that's what your that's what your sensation tells you. That's what bottom up processing would tell you. Maintain like knowing things like about shape or size constancy and using that information. That's part of top down processing. You know that doors don't just change shapes on their own. So you compensate and you ignore or you compensate for the change in shape on your retina. You don't believe it in a sense. you know it's still a rectangle. Okay, here's another example. This from the book. So they've taken these two photographs of the same objects. The first one has reddish lighting. The second one has greenish lighting. And because of color constancy, we see these grapes over here in the first picture and the second picture. We see them both as being green. We see the oranges in each picture as being orange because we know that's the color they are, you know, and yet the actual colors that you're sensing, it turns out that these green grapes in picture A are exactly the same color as this orange in picture B. But we don't see it that way. Like, even knowing it, you don't see it that way. And they've drawn this bar here, which is a constant color, to show you that it matches the grapes over here and it matches the orange over here. And even when you look along this bar, it seems like the color changes as you move from one picture to another. This bar over here on the right, it looks more orange. On the left, it looks more green. But that's just a trick um, because of the different lighting conditions. I mean, you're actually sensing um, different colors than what you're perceiving. So you're sensing these green grapes in A and this orange in B, that your sensation tells you they're exactly the same color. That's the raw data that comes into your brain. But it's your visual cortex that uses prior knowledge, top-down processing, and to actually cause you to see the picture differently. You see this orange as being orange and these grapes as being green, even though they're exactly the same color. Visually the same color. And so constancies can also cause visual illusions, like in this one here. I mean, it would be a very different world if we saw like if we could actually see these green grapes as being the same color as this orange over here. I mean, because that's what the raw data is telling us, but we just know it's not the case. So we constantly compensate because we know that oranges aren't green and grapes aren't orange. Okay, this one's interesting. I just like it. It's the checker shadow illusion. We perceive a checkerboard pattern of black and white alternating squares, and because of color constancy, we ignore the dramatic change due to the shadow cast by the green cylinder. Believe it or not, A and B squares are identical. It is so hard to believe, but I've seen demonstrations where you can remove each square individually and compare them. A and B are exactly the same color, and yet you cannot see that because your compensation, because of color constancy, we're expecting that the white squares are white and the dark squares are black, and so this is how we see it, because that's going to be the case in the real world. If it's actually a chessboard or a checkerboard, it's going to be alternating square colors. But and so we compensate and it creates this kind of visual illusion. I mean, I love this, and it doesn't matter if you know it; you can't see it differently. Like it's impossible to see A and B as being the same color, but they are. They're exactly the same shade. You know, they're identical in color, and I still find it amazing. Okay, here's one more, and this one's from your book is object constancy allows you to see both a stable world and perceptual illusions that you cannot control. Just like this last one, you can't control it, even though you know it's an illusion. Um, this is due to our constancies. Um, we see things the way we expect them to be in the real world. And so when you look at this here, this was an illusion created by the psychologist Roger Shepard. This illusion demonstrates the brain's automatic perceptual processes, even when we know the two tabletops are the same size and shape. And by the way, they are. Even if we have traced one image and placed on top of the other, perspective cues make us see them as different. So he does this, excuse me, he does this with the placement of the legs. So the placement of the table legs makes the first table look like a long rectangular table. We see it as a rectangle. And so that affects our perception of it. The second, because of the way the legs are placed in the second table, we see it as a square table. And as soon as our brain does that, oh, there's a rectangular table, there's a more of a square table, then it change, it kind of warps our perception of what's actually there. And it doesn't matter how many times I've actually compared these, you can't help but see the illusion. They do not look identical in size and shape. And in case you don't believe me, I've actually decided to demonstrate this one. So here I've created this blue shape here. I'm just going to slide it over. And during these pictures, I will not change it's the shape of it or the size of it all. So this is actually just a shift I do, and you can see that it's not exact because I'm not that good at this, but I almost got it pretty well. Like you can see, this represents the size of the table on the left. Now let me just rotate it. Once again, I'm not going to change it at all. I rotate it. Now I'm going to shift it again, and we shift it over, and you can see once again I'm missing a little bit, but you can see it's the same size. And whoops, I meant to go backwards there. So, it turns out, and this blue shape never changes. And you can see that it actually fits. And so you could do this on your own. You could trace and copy or whatever. But this is one of the things that people use to create illusions. The fact that we have consciences, and so our brain automatically shifts our perception of certain things due to our expectations. If we believe one table is rectangular and the other one is square, we don't expect the tabletops to be the same size. And so our perception is that they're different sizes. Okay, this will conclude learning objective 4 from module 4.